Hi everyone, welcome to my talk on channel duality. I'm Narayanan Rengaswamy, a postdoc at the University of Arizona. This is joint work with Henry Pfister at Duke. You can find the full version of this paper on arXiv. We would like to thank the organizers for selecting our work for a lightning talk at Beyond IID, and we would like to thank our reviewers for providing helpful feedback. Let's get started. So we are all familiar with the notion of code duality. So if you have a binary linear code, which is a binary subspace of all n-bit vectors, then the dual code is just the dual subspace. And this duality is simply based on linear algebra. Hartman and Rudolph used exactly this kind of duality to rewrite the sum over a code as a sum over the dual code. And using this, they were able to show that maximum likelihood decoding of a high rate code can be done very efficiently by just computing the sum over the dual low rate code. Now the question is there a theory of duality for channels rather than just codes? If we start with the binary erasure channel, which is a simple case, we are all familiar with the capacity of this channel, which is 1 minus epsilon, when the channel erasure probability is epsilon. And just by substituting 1 minus epsilon instead of epsilon, you see that the capacity of these two channels sum exactly to 1. And because of this, many researchers in the classical literature have considered BSC of 1 minus epsilon as the dual of BSC of epsilon. And this is basically an entropic duality where you have a sum of entropies summing to a constant. Therefore, the performance of a code over BSC of epsilon is completely characterized by the performance of the dual code on the dual channel. And one way to see this is if you consider transmitting a code word through BSC of epsilon, and let's say the erased indices are given by script E, then the ith bit of X can be recovered from all other bits, if cannot be recovered from all other bits, if and only if the ith bit can be recovered from all other bits in the dual setting, where you have a dual code word transmitted over the dual channel where the erased indices are complemented. So this can be argued using linear algebra, and in our paper, we give an entropic description of this. Now, Rennes then proposed the notion of a dual channel for the class of classical input quantum output channels, or CQ channels. So he proved tight entropic duality in terms of conditional entropies. So he showed, for example, as the main result, that the conditional entropy of the primal channel plus the dual conditional entropy of the dual channel sums to a constant, which exactly extends the BSC intuition. And he later combined this entropic duality with the notion of code duality and show that they go together. And he also discusses the notion of a dual CQ channel. The dual CQ channel is derived from the Stein-Spring representation of the primal channel, and it is done by a specific operation done on the complementary channel in the Stein-Spring representation. Now, if you consider the Shannon entropy, it is self-dual, which is what happened for the BSC. Now, we consider coding on the primal channel and secrecy on the dual channel, and these correspond to these pair of entropies, Hmin and Hmax. So Hmin relates to the probability of block error rate on the primal channel, and the secrecy metric is given by Hmax, which basically measures how far the secret is from the uniform distribution, so that if it's exactly the uniform distribution, then the eavesdropper does not get any information. So we consider this special setting of the primal channel being the pure state channel, where the input is classical 0 or 1, and the output is one of two possible pure states governed by this parameter theta. And the dual channel, using Rennes's notion, is the binary symmetric channel with this specific parameter, which is coupled to the primal channel. Now we show explicitly that the block error rate on the primal channel for channel coding on the pure state channel is exactly equal to the Bhattacharya parameter squared between the posterior and the uniform distribution for secret communications on the binary symmetric channel. So for secret communications here, the channel to the intended recipient is perfect, and the channel to the eavesdropper is the BSC. So we start with by discussing an entropic approach to BSC duality, then extend it to these pair of channels, and then use factor graph duality of linear codes to arrive at the final result. As an application, we consider this recently proposed belief propagation with quantum messages algorithm and use our duality results to show that it is actually quantum optimal for decoding binary linear codes on the pure state channel. And this is a big result because it shows the first explicit receiver that is quantum optimal on this channel. For more details, you can look at this paper, and this is a separate talk at Beyond IID. Thank you.